So hope we are good to proceed, and this is our today's lesson. I've said you are going to check under cardiovascular physiology, that is the function of the heart, and on the basis of the guidelines that have been outlined in the WhatsApp groups, what we've shared. So the very first one is circulation and pressure flow dynamics. So we're going to check on this one, and the analogy, I'm sure that you are friendly with this, and it's nothing like a strange thing, because barely from class 7 you've been doing the same. You've undertook some classes and learn on things to do with circulatory system, the structure responsible for the blood flow throughout the body, that is the component of circulatory system. You did talk about the arteries, veins, and the capillaries. Later on, out from the vessels, you did the component of blood. Coming back to high school form 2 biology subject, that is in Kenyan syllabus, you also undertake some of the lessons, and you learned about the external structure of the heart, the cardiac muscle itself, the cardiovascular system, and the internal component as well in terms of function and the disorders. Now today here we're just going to check on the circulation and pressure flow dynamics, and that is the basic behind what we are going to do today. So you can pay attention over the lesson, or you can as well wait for the link in the group. You can play the YouTube version of it, and then you still learn the same. So here today we have the objective as I had already outlined. We are going to check on general organization of circulatory system, cardiac structure and function, concept, pressure, flow, and resistance. We shall also check on the blood pressure measurement, factors are influencing the blood pressure, and we shall conclude with the conclusion part of it. So beginning from the very first part, we have to review the cardiovascular system. What you are able to see from your hand is merely a structured diagrammatical representation of what is inside your body under the cardiovascular system. So from my hand, you can see we have a key index. That is the good interpretation of a map require key. So the blood vessels, I think you can denote some structure like cables. Those are the blood vessels. The ones on the red side are oxygen rich. They are oxygenated blood. The ones on the light blue pale, those are the ones which are deoxygenated. So they are not rich in oxygen, but instead they are rich in carbon dioxide. I'm sure that one we are well conversant with. We also have some capillary bed, that is of the lungs, where the gas exchanges occur. So we have the two pairs of lungs with the different lobes. You always know that we have the left lung, which has only 2 lobes, and then we also have the right lungs, which have the 3 lobes. So temporarily, this heart on the center is supposed not to be here, but this is just a structure. So don't get confused. The heart is supposed to be located towards the inside the left lungs actually. And so you need to see we have pulmonary arteries, which is connected to the lungs and heart. Its function is to supply the blood, that is deoxygenated blood, to the lungs so that they can be reoxygenated. Just the same knowledge that you had in high school and class 7 knowledge also. Then from the lungs we also get pulmonary veins, which brings into the heart the blood which has already been oxygenated. And then away from that, we have the main artery, that is aorta, going downwards and then bathing the entire tissues on the systemic circuit of the body. Then from the body, the blood, after it has already been used and oxygen consumed, it has to flow again back to the heart. Now this flow will go into the heart via vena cava, which is divided into the inferior and the superior vena cava. So that is that. Just an outlook of the entire thing, just like a mind mapping. So let's check on the internal structure one. From your hand, I'm sure you are able to see this. Are you able to see what I'm presenting from your hand? Anybody to say anything? Are you able to see my presentation? Hello? First of all, am I audible? Is my presentation clear? Thank you so much, Juma. So let's proceed. Now you can see from this aspect, remember the cardiac, actually at most the size is always assumed to be the size of your fist. That is the reality behind the size of the cardiac. But now then, according to the illustration that we normally pick from the textbook and so on and so forth, the heart tend to be much bigger. That is just deduced for you to be able to zoom in and see on the structural and microscopic basis in a very real size. Now, at most, we have many other conditions that you will also learn in clinical phase and studies, and you'll understand that there are many relevant cardiovascular disorders that are also important to know, like the deep vein, the thrombosis, or the varicose vein, all those, the DVT, the coagulation profile that is now disseminated intravascular coagulation, what we also call the DIC. So all these ones, they normally just relate with the cardiac. Don't forget about hypertension. So the same apply. There's another typical condition that is very key, and therefore you really need to know the exact location of the heart. You also need to know how it looks like, and that is why it's always recommendable that if you have a minor surgery or autopsy taking place in your clinical area, especially in the morgue, you're expected to rush and see for yourself what is the heart, let alone the variation or maybe the textbook appeal, what you are able to see from the textbook. At most, they are not exactly the same with what you are going to see inside the real body of a human being. So when you go there, you can see there are different types, the coloration of the heart. The person who is suffering from the hypercholesterolemia, familial disease with a lot of cholesterol, the outer part of the cardiac, or what we call the pericardial membrane, is always sheathed with yellow, like lipid structure or maybe substances. And like with someone who's frequently attending to exercise routine, whereby the cardiac is clean and the vascularization are spotable. So such a management, let's say nowadays we even have the cardiac transplant and so on, so the catheterization of cardiac, bypassing when you have a thrombus blocking coronary artery, those are the basic part of it. And importantly, you're supposed to go to the morgue to analyze and also to get the look of the entire thing, so that at least you have a clear picture with you. From there you can see we have what we call the special cells, the sinoatrial node, right, the atrioventricular node, the Purkinje, the right bundles branch, the RBB, we call it that, the Purkinje fibers. All these ones are going to be communicated when you are going to check on the electrical conductivity of the heart, how the impulses are intrinsically stimulated and how they run for us to have a complete cardiac cycle. But within this structure, you can see we have, now normally when you're in class 7, you could just see some outlet which are countable, like Udaona, pulmonary artery, pulmonary vein, they were just, but on the top here you can see we have a very rigorous connective of several vessel-like tubes or tube-like vessels. So these are what we refer to as the aorta, during those times of amateur. Like we had one sample of pulmonary arteries, but here you can see they are diverted. There are ones which are running toward the left lungs, and there are others which are going to the right lungs. So we're going to check on all these ones, and you can see the details are very important, and so you still need to be interested in this vital organ. Similarly, there's another photo here presenting the cardiac heart, the heart internal structure too, but now this one is not that oriented in terms of photographic in a way. It is more of diagrammatic than photographic. Now in this illustration you will be able to see the real structure in microscopic analysis, and everything is already labeled. From your hand, I'm very sure that you are able to see aorta labeled, you are able to see the pulmonary valve, tricuspid valve, the right atrium, the inferior vena cava, the right ventricle, the papillary muscles, orifice of coronary artery, and so left ventricle, aortic valve, mitral valve, lateral, left atrium, and pulmonary artery. Are we together up to there? Am I audible?
Yeah.
Okay, thank you. So these are just outline of what you've seen, but don't forget we have these things which are called the papillary muscle. They help to stiffen the valves. And we have some valve conditions or the valve disorders, which we are going to check on later when we'll be doing clinical video lessons. When we'll be checking on clinical pathology, congenital anomalies of the heart, so that is cardiovascular congenital anomalies. We shall also check the conditions or disorders related to the valves, like mitral stenosis, right? And you see how they have repercussion on the entire human body. So away from there, this is a presentation of a photographic film, right? This one is an ultrasound image. Actually, it gives you a measurement, which these are the interpretation that you really need to learn, because as a clinical officer, medical officer, you will be assimilating more of this one than even the norm, because for us to do a management on a case, we have to first diagnose, and some of the techniques are like just the radiology and all those investigations which are necessary on the radiology. Can be CT scan, can be ultrasound, can be MRI, All those ones are significant. But the most key thing here that I need you to understand that these measurements are very key, because you will know whether we have cardiomegaly, and if it is cardiomegaly, is it affecting the atrium on the left side, or the atrium on the left side, or the ventricle on the other side, or is it affecting the aorta as large? So it is something you need to know in terms of the real dimension, and therefore anything which is deviating from the dimension, you will know there is enlargement, or we have a tumor, or we have, we can have hypertrophy, hypertrophy. That is just but an adaptive mode of the cardiac in case somebody suffers in a detailed array of hypertension, so any other myocardial disorders. 4-chamber view cassette AV ring, anteroventricular ring. So this is just a 4-chamber view chamber. You can use that, and these are the normal lay images that we normally use. So we normally use the 4-chamber to indicate in a conscious way the location of the atrium, the left ventricle and auricle, right ventricle and right auricle, the septal alignment. You will get to know this one, and it's very, very important if you use YouTube to read that. So let's check on the blood pressure, flow, and resistance in the cardiovascular. Beginning from the blood flow, there is a formula there from the physical formula. You see the F is equal to delta P. That is the flow is equal to delta in the changes in the blood pressure, or over the resistance of the vessels. That is what it does there. So the flow, the force behind it, or the blood flow in general, is changes in blood pressure of the resistance, which is equivalent to pressure 1 minus pressure 2 over the resistance. So we're going to check this one in details. Right now they're just in symbols. That is why they look. But if you're a physics student or physician in a way, you are good in this. So let's see. Normally, what is presenting there, that is a vessel, blood vessel actually, just like a tube. So we have a pressure gradient, the P1 and P2. Pressure 1, as it goes, changes to P2. On the course of the movement inside the blood vessels, we have what is resistance generated from the wall of the vessels. That is the direct opposite force that is caused due to friction between the blood flowing and the endothelium lining of the blood vessels. So we have a maintained blood flow, yes, but we have some basic resistance analogy. So that is what will now give us P1 and P2. So P1, if it was strong, P2 will be low because of the resistance. That resistance will tend to increase the pressure of the cardiac, because the heart now has to pump blood to pass through the resistance in an easy way. So flow dynamics, we have to define the following terms. First, cardiac output, so that you can know them first before we proceed. And cardiac output is the amount of blood ejected by each ventricle per minute. So each ventricle, their total blood per minute is what we call the cardiac output. Then stroke volume, amount of blood ejected by each ventricle per beat. Per beat, that is by complete systolic. Moyo wako, I don't know moyo and roho, but I suppose moyo and roho. Anyway, we are in a group. Swahili, I always have this problem, but I think you guys can tell me. What is moyo and what is roho? Which one is cardiac? Moyo is the cardiac, eh? Thank you. Thank you, Faith Chabet. Sometimes I read.
Roho is the soul.
Oh, Ro is the soul. Okay, thank you. So, let's assume, I will just forget tomorrow, but I'll try to remember that. I normally get somebody telling me that I'll mistake them. So, stroke volume is just more like the same with the cardiac output. But now cardiac is generalized term for what comes out from both ventricles per minute, regardless how many beats have gone within the minute. On the other hand, the stroke volume is the amount of blood ejected by each ventricle per beat. Not now per minute, per beat. Now, we have a preload. Preload is what we call the venous return. And venous return is the total volume that comes from the systemic circulation back to the heart. Be it the systemic circulation was from the brain, be it the systemic circulation was from your legs, all the other body parts, the peripheral, circulation. All those blood coming back and returning back to the heart is what called the venous return. Then we have afterload. These things are very tricky, so you need to know them. Afterload is always equivalent to resistance or the total peripheral resistance. And for us to have resistance, you have to know the pressure generated, and what are the quantifying in terms of the blood, the vessels, the blood vessels and their walls. So resistance is just that blockage of blood as it flow over the blood vessels in the circulatory system. So the resistance is what we have after load. So even the heart will be influenced by the resistance. When the blood comes back from the entire part of the body and then it flows back to the heart, this resistance will reduce the pressure in a way. So that load which comes as consolidated with the resistance, that is what we call the after load. And I will encourage you go and check in YouTube the mechanism of afterload, and you'll see how it's demonstrated in an animated way. So let's check on the flow dynamics still. When I talk about flow, when we are going to apply this on systemic circulation, so flow will mean the C, or the cardiac output. Then we'll have a driving pressure, that is always the arterial mean pressure or mean arterial pressure, denoted by PA. So when I say flow, I mean the cardiac output, what comes out from the heart ventricles. And when I say the pressure which diverts the blood, I'll talk about the PA, the mean arterial pressure, and I'll tell you how to find the mean arterial pressure. And then when I talk about the CVP, central venous pressure, and if you are there, what do we understand by central venous pressure? Because for us to have the driving pressure, that is what pumps the blood all over, what makes the blood flow, we'll have to have the PA and then we minus the CVP, the mean arterial pressure minus the central venous pressure. So first of all, let me ask you, where do we have the central venous pressure, and which part of the body can we use to measure the central venous pressure? Anybody with the answer? Anybody with the answer? Okay, assumingly you will learn about that and then you get to know it. But you know the central veins, where to get them, right? Yeah, you know the jugular veins and all that. So then when we talk about resistance, we are going to determine resistance by total peripheral resistance. So resistance is just general, the TPR. So I've said flow, if we mean flow, we'll be talking about the cardiac output. Driving pressure, we'll get it by taking mean arterial pressure, then subtract the CVP, and the resistance is that one. Then if we use this one and equivalent into a formula, we shall now have a triangular formula, which is cardiac output is equivalent to arterial mean pressure minus central venous pressure over the resistance, or the total peripheral resistance. So this one now can be intertwined. I'm sure you can manipulate this one. If you want to find L in your maths, I don't know, was it substitution or ratio and proportion, whatever. If you want to find resistance, you can just make the subject to be the resistance and the rest will just fix in. So this formula, you can remain with it in your image so that at least at long you can still configure and adhere to what is here. So for instance, for us to know or get the the central venous pressure, which is equivalent to the entire output, or O, we're gonna have that one as a denoted. So since the central venous pressure is O, the cardiac output will now be the mean arterial pressure over the resistance, or we can use that one to form the final formula that will give us the mean arterial pressure is equivalent to cardiac output multiplied by the resistance. So to mean we can get any, if we want mean arterial pressure, we can make it the subject and then we cancel the rest and sort and get the formula. So this formula, you can generate them wherever you want them, whatever you want, as much as you have. Thus, this part, thus, right? That is that. So let's proceed to the basic part of this. Now the homework is you are expected to read the Bernoulli theory and the law. This Bernoulli theory is in the medical students arena website. Click programs. I'm sure programs won't request any login permission. Then you go to clinical medicine year 2. Yeah, then we have clinical pathology. You will find all the sequential theory that will aid you to learn about the Bernoulli theory and the law itself. So let's check on the flow of blood in vessels. We have 3 flow patterns which are recognized. We have the laminar, turbulent, and single file. We have the laminar, turbulent, and single file. When we talk about the laminar flow, is a silent one and it occurs in normal arteries, that is arteries without diseases. It also occurs in normal arterioles, venules and veins. They are silent up to a critical pressure above which it becomes turbulent. That is, it remains silent a bit up to when it is somehow disturbed or distorted in a critical way, it becomes turbulent. So laminar can change to turbulent if the normal orders or parameters are fluctuated or maybe affected. So on the turbulent flow, they are always noisy, occurs in the ventricles. Yeah, that is at most the ventricle. Why? Because the ventricle is where the blood flows in a very low pace, not that very low, but low in a way. And also they are symmetric or maybe aided by blood vessels, whereby the noise and turbulence are because of the blood valves, the valves itself, the valves which are present in the ventricles. Normal single file flow occurs in capillaries only, and you see that one presented with the diagram below. Now blood, so the first A, these are laminar flow. You see there is an entrance zone, then parabolic profile. Then we have the single flow which occurs in the capillaries, that is plasma bolus. So you see the other one. So let's check on how we can measure blood flow, measurement of blood flow. First, we can use electromagnetic flow meter, and we have already indicated an homework around. You will read more about this method at your own free time. So we have Doppler flow meters, indirect methods such as the fixed principles. The indirect method does not require you to use any instrument like Doppler flow meters. Instead, you use a theory which explains if this one happens, then this one is like this. So that is an equation like, but it's suggestive, not directly being done in a practical aspect. That is indirect method. So we have fixed principles. We have paraminohyperic acid. We have the venous occlusion plethysmography, Ketty's tissue clearance method. All those ones are important in determining or measuring what we call the blood flow. So away from that one, there is a road homework that you have to do. Read more about these methods. Hemodynamics in the artery, that is another thing that you also need to know. And here we have to define capacitance vessels. Capacitance is just capacity, kiwango ambayo blood vessels inaweza beba damu, si maji. Capacitance vessels, for instance, vein, they hold large amount of blood vessel, over 50% of circulating volume. Then you talk about resistance vessels. These are small arteries. Because they are small, their lumen are narrow, and because of that, the blood tendency of flowing is resisted. That is why they have high resistance. That is what we call resistance vessels. Now, high pressure system, those are the arteries system. Then low pressure system are the systemic veins, pulmonary circulation, and heart chamber. I'm trying to say that high pressure system, they are artery to mean the blood flowing from them are directly linked to the heart. So the pumping mechanism, the force and the pressure is directly distributed, and so it has that direct effect. With the heaviness of the pressure, you will feel them in the artery, and most of them are located inside your tissue so that they can be away from any cut or on the superficial, not tall. So for a tall, that is for protecting that blood, because if at all an artery is located externally and then you end up on a structural damage, you will have overbleeding and you will die of a shock or something next to that. So we have low pressure, that is systemic veins. They are however outside in your body. We have them several. We have the saphenous vein, the femoral vein, right? We have the midcubital veins. They are all over our body, yeah. The facial vein and facial artery are also located in our head, and so on and so forth. Hemodynamics in the artery, that is in hemodynamics too. And then let's talk about hemodynamics, just the blood stability, how they change and fluctuate in terms of blood flow and blah blah blah. So let's talk about hemodynamics in the arteries too. Waveform of the artery, pressure pulse, arterial pressure oscillates or fluctuates, volumes and speed of ventricular ejections, rate of run-flow through resistant vessels, arterial wall distensibility. All these ones will aid in fluctuations in the blood. So we have volume, speed, ventricular ejection, how the blood, the speed at which it moves at. We have the rate of runoff through the resistant vessels, arterial wall distensibility, that is the ability of the arterial to be, to conform to the pressure, how they can distance, that is increasing in size and reducing in size. Pulsatile flow. What is pulsatile flow? That is how the pulse tends to maintain its rhythm throughout the blood vessels. So how that one is already indicated, is not well understood, but maintains optimal function of the tissue. because almost that pulsatile flow is what maintains the blood vessels open and enable even the innermost or the internal tissues to receive the blood, which is rich in nutrients and oxygen. Now check on this waveform. We have systolic pressure on the top, dicrotic notch, that is at the linear deviation. Then we have diastolic pressure immediately after dicrotic notch, that is at 120 millimeter of mercury. We'll have the dicrotic notch. For us to have the mean pressure, you see, we dive over, we find the topmost, that is the most systolic pressure, and the most diastolic lower pressure. So like we have in between the mean pressure, then we have our weight made and the pressure, then the pulse pressure is the difference between the top systolic pressure. We subtract the diastolic pressure from it. That is when you get the pulse pressure. So you can read what is there. Pressure wave in human subclavian artery over 2 circles recorded by an electronic pressure transducer, and the mean pressure averaged over time is the pressure at which the area above the mean equals the area below the mean. Insert shows abnormal wavelength in aortic valve stenosis, and I'm sure you know aortic valve stenosis, that is the narrowing of the aortic valves, and aortic incompetence, that is when we have a malfunctioning of the aortic valve, that is when they present, we will have or emitting or maybe variable minor waves on the descending limb caused by the reflection due to any condition which is associated. Away from that many English and all that blah blah blah, you can come back and share the same notes in your WhatsApp group for you to analyze and learn. You can also have this pressure waveform for your own understanding of what we are learning today. Now let's check on the hemodynamics in the arteries 3. Here we are going to check on the mean arterial pressure, and we are going to see how we can relate them with the diastole, systole, and how we can deduce the mean arterial pressure from the diastolic pressure and the systolic pressure. So away from that, blood pressure spends relatively more time near diastolic pressure. That is why when you are going to calculate the mean arterial pressure, mostly our calculation will be talking about diastole. And that is what you can see. Therefore, thus, mean arterial pressure denoted by P with a small f equivalent to the diastolic pressure plus, in bracket, systolic pressure minus diastolic pressure. So what remains here is what we'll use, because what you can see from this statement is that blood pressure spends relatively more time near diastolic pressure than systolic pressure. So even in this systolic pressure, we still subtract diastolic pressure. Then we divide by 3, taking in consideration that we compiled the 3 parameters, that is the pressure on the diastolic, then we subtract the pressure of diastolic again from the pressure on systolic pressure. So the pulse pressure on the other side, the way I told you just directly, you take the systolic pressure, you subtract the diastolic pressure, and the pulse pressure depends on the arterial compliance, that is how the blood vessels, the arterial blood vessels receive and reciprocate the pressure. They also vary or depend on the stroke volume, that is the volume ejected from the cardiac ventricles in a minute of a beat. In a single beat. It also varies or depends on the ejection rate and the runoff as well. Viscosity and blood flow. What you know that the most thing that influences the viscosity of the blood is the red blood cells. That is because of their discoid phase and what their component entail. So the larger numbers of suspended red cells make the viscosity of normal blood 3 times as great as the viscosity of blood. And the viscosity of blood increases drastically as the hematocrit increases, as in example polycythemia. What is the polycythemia? What is that? Who can tell us what is that? Okay, let's proceed. They will watch over this one. Okay, normal blood pressure in circulatory system. You can see using this curve. We have aorta, we have large arterial, we have small arteries, we have arterial. You can realize that in the aorta, we have a very stiff or high pressure in arteries, that is aorta, large arteries, small arteries, and arterioles. Then from there in capillaries, the pressure now tends to reduce as it flows to the venules, small veins, large veins, vena cava. Then it raises in pulmonary arteries, arterioles, capillaries, venules, pulmonary veins. That is how they range. Away from there, measurement of arterial pressure. What we do, we can use direct method. By first method to be used in the measurement of blood pressure, and then we can use indirect method. Like now, indirect methods are like the sci-fi manometry. The ones which we use can be mercury manometry, all that you can see on those. Then River Rocky. The River Rocky is a curve over brachial artery, and this is mostly used. The River Rocky is the one which is used in the clinic and the casualties for quick denotion of the blood pressure. Curve inflate to obligatory, the radial pulse flow sequence of sound heard, and then use both. So this is example of what I was telling you. Yeah, the River Rocky. The River Rocky. The River Rocky. You can see we have an inflatable balloon, then we use that one. Yeah, we use measurement of blood pressure, dashing represent compression, brachial arteries under the sphagometer curve. The curve pressure is controlled by the rubber bulb, and then they measured by the mercury column. And then we'll have what we call the Korotov sounds, begin when curve pressure is just below the systolic pressure, and it also disappear when the curve pressure is close to the systolic pressure. So where it starts, that is systolic. Where it disappears, that is dystolic or diastolic. Measurement of arterial pressure, on the other hand, we can also use curve pressure just below systolic, and that is what I've just said here. You can as well read that one if it is necessary. So blood pressure, what is normal blood pressure? Pressure is labile over 24-hour period. Pressure normally change when I say it's labile over 24-hour period, and we also measure it in those units, either millimeter of mercury or in kilopascal as standard unit of measurement. So we are finishing blood pressure factors affecting it. Age can affect the blood pressure. Age increases with age, pulse pressure also increases in the same. So sleeping also can make the pressure to fall. Can even fall below 80 and 50 millimeter of mercury, because your body and the heart tend to relax from any physical activity. Gravity, it has a direct and indirect effect. Emotion and stress also affect your pressure, and the factors can be respiration, Valsalva, maneuver, pregnancy, full bladder, etc. So that is that. So blood pressure in different parts of the circulatory system, I'd already indicated that one. So I wanted to see this one. Factors influencing arterial blood pressure, we have stroke volume plus heart rate will give us cardiac output. Cardiac output times, heart rate times stroke volume will give us cardiac output. Then cardiac output times total peripheral resistance will give us arterial blood pressure. So factors influencing arterial blood pressure is equivalent to, this is now what we have here. This is now what we have here. Neurohormonal factors, tissue factors, vascular factors, and vascular anatomy. So go and relate on how this affects the entire system. Wait a minute. So we have, let's talk about them. So first of all, neurohormonal factors. These are secretion like the catecholamines, which will speed up your, the transmissions of vasoconstriction, enhances mediators, and so by that we can have the retention of sodium and water, resulting to increase in blood volume, causing preload to increase, that is a venous return, resulting to systolic volume and cardiac hold, and then we have mean arterial pressure elevated. Similarly, neurohormone can as well result to venous compliance, resulting to preload increase as the cycle continues. A neurohormone cell can affect the inotropy, that is the increase in the cardiac effect in terms of positivity of cardiac pulsations, and that brings cardiac output, and that one also applies. Similarly, it can hormonal factors can as well attribute into heart rate. Heart rate brings in cardiac output in elevation, and then mean arterial pressure also. So all these one, tissue factors, vascular anatomy can bring that schedule. And for more, you can inquire through internet. Vascular resistance. Homework, go and read about the Postulus and Laplace laws. Laplace laws outline blood vessels are distensible, thus width of the given vessel depends on 1. Blood pressure, 2. Surrounding pressure, 3. Tension in the wall. That is all about the Laplace law. So that is the end of what we had about the first topic of our today's lesson. That is under circulation and pressure flow dynamic. Thank you, and you can always follow us, and don't forget to subscribe in our YouTube channel.